Okay, guys. So we're going to go
commercial, but whatever,
and with some more concepts. Hide this. Right, so now we're going to go through the kind of consensus layer and how that can be configured and changed. Especially for this side, use presentation mode if you want to use it later. It's got a lot of animations. So consensus has two different sections in EOSAO. It has the core block consensus and how those synchronize across the network. And that's done with a supermajority consensus. You need 2 out of 3 plus 1 of the defined nodes. This is called asynchronous BFT, a term that I think they have invented. And it's done through some of the plugins in the core node software, which we're not going to go into so much. And you have the second part, which is the voting and election of who is going to be the people who create blocks. And now this is all defined in smart contracts. So this is completely customizable. So you can create this in a way that so the default here is using delegated proof of stake, a consensus mechanism I'll explain in a second. But you can rewrite all of that to actually have proof of authority, proof of stake, hybrids, democracies, all kinds of different consensus here. So basically, these two different protocols for consensus are in different parts of the node. The production part is run by the core software. That's the block synchronization part. The election of who gets to be the block producers is done in smart contracts, right? And that's written in tables in the USAO database. And that makes this part here very transparent. Everybody can see what's going on. So this part of the consensus does not happen off-chain. It also makes it completely upgradable and customizable. So, yeah, the USAO system contract, this is provided by them. This defines the default consensus mechanism that they provide. And delegated proof of stake is a system where you vote with your tokens in the system, with the system currency. You vote, and depending on your weight of how much you vote, that will vote in who's supposed to be creating blocks. So the way that works is I have an account called EOS Authority. I register myself as a producer, say I'm going to be a block producer in this system. I would like to be. Then another account, so a regular token holder, whatever in the system, calls another action called vote producer, and they vote for up to 30 producers that they would like to be the ones that participate in consensus. And then that algorithm determines a ranking of who has the most votes in the system. And your vote is weighted by how much tokens you have. Make sense? Yeah.
What will be the advantage for me to vote for one entity or another?
So you would vote for block producers that you trust to run the blockchain properly. And if you see that they're not, then you would vote them out. So this gives the flexibility to have honest block producers. That's the whole point of this.
And how can I see this?
Well, if
is there like a ranking?
Yeah, if you're techie enough, you could run a node yourself that audits the blockchain and check if they're doing it properly. Additionally, there are quite a few public tools out there that show statistics of how well block producers are running the software. And there's more to block producing than just producing blocks. There's a whole governance aspect of EOSAO chains, depending on how it is, that is also part of their responsibility. So you have to look at those things as well. So for example, in your private blockchain, I'm not sure if they would use delegated proof of stake, but perhaps the people who run the network they're also responsible for upgrading the network. So if you're seeing that the block producers you vote for are not upgrading the software as they should be, then you might also vote them out. Things like this. Block producers also have some privileges, and if they're misusing those privileges, you might also vote them out. And there are generally public tools that allow you to see this if you don't want to run a node and see it yourself. But basically, in theory, anybody can audit the blockchain and figure this out at a technical level. Right, so you vote in for the top 30, for up to 30, and that action itself, vote producer, then goes and calculates who will be the block producers with the most votes. You can see that here. This is the number of votes that each of them has. So you can see at the top, this is for the Telos blockchain. This one here has received the most votes of all of the block producers. So then every single block has this action. As the first action of every block, this is triggered. It has to be. This is part of the protocol. This specific action. And it says that every 1 minute, it tallies up all the votes. It selects the top 21 block producers. It sorts them alphabetically and puts them into a schedule. And it does a few other things. So then that schedule here sets up who is allowed to create blocks when. Right? So there's a schedule of 21 block producers. Each of them is given a round of 12 blocks to produce blocks in. After the first block producer's round is finished, they create 12 blocks. They hand it over to the next block producer who creates the next one. So this is how it's defined in Delegated Proof of Stake in the system contract. So this can be totally customized. So in Delegated Proof of Stake, they select the 21 most voted for block producers and set them in the schedule who is allowed to create blocks.
So that schedule of 21 means that when the schedule is set up or decided, the 21 will get a turn on producing blocks.
Yeah, and they should create a block. They're obliged to create a block if they become in the set. So, and then regular users can and should monitor if their voted block producer is creating the block correctly. Yeah.
And, what if, for example, and you said that this triggered action is on every block?
Yeah.
So there's a tally of voters, select top 21. Let's imagine a scenario that one of the block producers gets attacked. And it's currently number 5 to run on the schedule.
Yeah.
Each time a block is produced, there is voting, but it is already scheduled to be number 5.
Yeah, so if they can't produce a block, then that block just gets skipped. Either they're attacking the system or somebody else is. We're going to go through that in a bit. What kind of happens there? Another question?
If it's scheduled, then I know when I'm going to produce block.
Mm-hmm.
What if I'm corrupt?
Yeah,
right?
so
I'm number 20 and I'm saying,
so you still have to receive supermajority consensus. If you're attacked, you still you still create a block. If you break the rules, nobody else will sync it. So you still are enforced by the rules in the system. You can't break those rules. Otherwise, nobody will sync the block you create.
Half a second is enough time to.
So I'm going to get to these questions. So this first section, the election of block producers, this is all on-chain through the system contract. If you want to look at EOS Studio, you go to the EOSIO account. That account there has all of those functions. You can see what actions are happening on it. And you can see its code. So what is interesting about this is that onblock function sets the schedule. And you can change that function to set the schedule to whatever you want it to be. So this is where you can define if it's a proof of authority network, so that just means a permission network, or if you want it to be proof of stake, you could build a democracy by changing onblock, whatever you want to do. And its only limit is whatever contract programming is available in C++ and on the blockchain. So lots of different modes are possible here. All of this consensus is done on-chain through a transaction which can be mathematically audited. It's very transparent. You can see this happening. And lastly, we're going to go into how contracts upgrade. But basically, the system contract is also upgradable. So you can change consensus on the network as needed, and only if you're in consensus with the current parameters. So this is quite different to most other blockchain systems. So Bitcoin, if they want to change consensus, they would have to hard fork their software. This doesn't have it in the software. This has it in the contracts. You can change consensus through contracts to customize the blockchain at the beginning or as you're running it, which is quite cool. So the net, yeah.
Sorry, just one question previous slide. So actually there's like block 1 to 12, 13. 13 is from round 2 onwards.
Mm-hmm.
But only one of the blocks gets approved, right? How does it?
We're going to ask that question in a bit. Yeah. So this is generally what kind of the network topography of a decentralized EOSAO blockchain. You have the core network of who is permissioned in the schedule to create blocks. Each of them has a very lean, very high performance server that they run the software on. And they usually connect to just one or two of the nodes outside of the network. And these nodes send the transactions in. These nodes outside the network run some heavier software that does like an HTTP API. The nodes in the middle, their only task is to create a very tight mesh of connections with them to be able for them to synchronize extremely quickly these blocks in consensus. Like I said, there's two parts to consensus. There's the on-chain part, which defines who is allowed to participate in consensus. And then there's the actual block consensus part, which doesn't know anything about who is allowed to produce blocks. It just gets that from the smart contracts and uses it. So, so the way that works is it uses a supermajority, a 2 out of 3 plus 1 consensus. So 2 out of 3, so 66% of whoever is permissioned, plus 1, that is the amount needed to achieve consensus. The way that works is a block producer at their given slot time creates a block. Once that supermajority of block producers has built a block behind it, it's considered irreversible. Okay? So on EOS Teros, 2 of the decentralized networks running EOSAO, they have a 21 block producer schedule. So that supermajority, 2 out of 3 plus 1, is 15 block producers. That's the amount of consensus needed to get to an irreversible block. And in EOSIO, they all use 12 block rounds. In the next slides, we're going to go through an illustration to show this whole process. And it's only going to have 4 BPs, which means you need 3 to create consensus, and just 2 block rounds. And we're doing that so that I don't have to put 12 block producers in a slide. So this is our illustration network. We've got 4 core BPs that are permissioned to participate in consensus. They're in a schedule. So this is the schedule down here. So the process, the kind of workflow is that these core block producers, once they know that they're in the schedule, they start creating very tight mesh connections directly between them. And then they each create at least one connection to a node outside of that core. And then the rest of the network all hooks up to each other as well. So now we have a user who wants to send a transaction to the network. They send it to probably whichever node they decide to, or maybe their closest node, or whichever, or maybe depending on the DApp will decide on what node to connect it to. That transaction is synchronized across the network using something called a gossip protocol. The gossip protocol basically says, tell this to everybody around me. So it just sends that transaction on until it ends up in the core block producers. So this process keeps happening. Other people submit transactions to the network, and these nodes collect transactions, these core nodes. Now at some point, somebody makes a block, and what they do is they collect the transactions that are pending, that are not in a block. They put them into a group called a block, right? And that here is the first block producer here called EOS Authority. So they create a block with those transactions. Those transactions are just ordered by when they're received. So now they create this block, and they send that block out to all of their peers. Firstly, the ones in the core network. And those peers firstly verify the block. They check it doesn't break any of the rules, and then they add it to their history of the blockchain. And then once the block's synchronized to the core network, they'll start sending it out to the nodes around them, and eventually the whole world will have seen that block. So next in our schedule, we have a two blocks per round. So the same block producer will create the next block. Again, sync it and send it to the rest of the core producers, which will then send it to the rest as well. So next in line there is another producer next in the schedule. So that's this one here called EOS stack. They will create the next block. And only they are allowed to create the block at that slot. And they will just keep creating blocks and sending it around the network. First, they do the core block producers, and they'll keep syncing it. Remember, if they break the rules, they'll be able to be cryptographically detected, and the other nodes will not synchronize. They will not accept the block, and they'll just stop synchronizing. So now, once we get to the next producer, right? So EOS whale, as it's called. They create the next block. Then the next person in the schedule. When they create that block 5 in this setup, that means that there are now 3 block producers, 1, 2, 3, that have built on these first 2 blocks. So that's the 3 out of 4 consensus has now been achieved on those first 2 blocks. So those first 2 blocks are now considered irreversible. They cannot be changed as defined in the protocol. So this is basically the process. They created their second block. Now when the next block producer, the fourth one, creates their next block, number 7, that will make block number 3 and 4 will be considered irreversible. Right? They will have achieved that 3 out of 4 consensus. Hopefully that makes sense. Any questions? Yeah.
So it's, they get locked one at a time. 2 of them appeared there, but they get locked one at a time, right?
No, so both of these become irreversible at the same time. Yeah, because both of these now have 1, 2, 3 block producers on top of it who have built a block behind it. Yeah.
So that first one is responsible. The first one is responsible for 2 blocks.
Yeah. So block number 3. So at the point when 7 is created, then you've got this block producer has created it, plus this one, that's 3. When number 4 is created, it's also created by EOS stack. So then you've got 3 block producers.
I see.
Yeah. So this is the production process. So these nodes, they receive pre-validated transactions. And I say pre-validated because usually one of the nodes outside of the core has pre-executed and sent it back if it's going to fail. So that's kind of a load balancing operation that's done in the network automatically from one of the connected nodes it's connected to. So they receive these transactions, they order them by when they're received, and then they group them into this block and execute them. So the first thing they do in the block is execute the onblock action. That has to be the first action in every block. If you don't do that, then nodes will not sync it. Then they execute the transactions they've got in their group by order of when they were received. As they do that, they're updating the EOSIO database as needed and doing resource accounting. They're billing people for RAM and other things that need to be done, which we'll go into a bit later. So then after that, there's a 300 millisecond gap. So that's all done in 200 milliseconds. That's the time frame they have. In 300 milliseconds, they have that time to propagate it to the rest of the network. This is half a second what goes on every half second. So right now just keeps going. It's extremely fast. So these there's a lot of parameters that can change this. This is, I'm not sure if this is done on-chain or not. There's a few parameters that can modify this if you want. So people have, I know, experimented getting this up to like 400 milliseconds, and then you're able to make the blockchain really, even more scalable, like twice as much time. Twice as much time to build a block, which means you can put twice as much data in it. But then the blocks are bigger, and it means that there's more consensus failures. So that's kind of the balance here.
Right. So the disadvantage of making the block so small and making it go so fast is that the amount of information in the block is also very minimal.
Yeah, and it also means that this balance, because this is only half a second, you have to do both these tasks in half a second. And you can see, like, they've chosen I mean, this is the default. You can make it whatever you want. But this amount of time is needed to really propagate it across those at least 21 nodes.
Is there a maximum size of the block?
It's half a second as defined by the protocol.
What's the size?
No, there's no maximum size in megabytes. No.
So
I
each
mean,
block should only contain like 6 transactions.
No, I think you can get much more. No, I mean, you can get
Because it will-
thousands in a block.
Because you mentioned that each transaction gets max 30 seconds to execute.
Yes, but most transactions execute in sub a millisecond. So then you can get thousands of transactions in a block. So then everybody else who's not the slot block producer, they're receiving blocks from other nodes, and they just receive them as they get them. They're blocks. Their job is to just execute all the transactions. They have to make sure onblock was done first. They validate that it was done according to the rules. They update the USAO database and resources as that's happening. And then if it completes all these rules, then it synchronizes it, adds it to their blockchain. And then they wait for the next block. So that's everybody else.
There happen like one of the producers has like a lag and then they
Yeah.
trust the...
So what can happen in this network? So these are kind of the 3 rules that govern how to synchronize. Okay, and we're going to see that definitely consensus does fail in a acceptable way that still allows them to synchronize. So firstly, the first rule is that the longest chain with the most irreversible blocks is the correct blockchain, and that allows them to come to consensus. So BPs are only allowed to produce in their scheduled slot, and they're also only paid for blocks that are actually produced, that other people come to consensus on. Otherwise, so now this is the normal operation as we saw before. So these guys all create blocks one after the other. There's a handover between each block producer that happens smoothly, right? But sometimes a node might miss a block. Half a second is not long. If they have a high enough latency to the rest of the nodes around them, they may just not get their block to enough people in time to get them to synchronize. This could happen because the wire fails, their server fails, whatever it could be. It often happens during a transition from one block producer to another. So this does happen. You can also get cases where they miss a whole round within them, and the next block producer just doesn't see any of the blocks the previous one creates. So they go ahead and create their scheduled block, having not seen these, and the network just keeps going because nobody saw these blocks. Those are just missed, and that's fine. This is part of the normal operation. Because this is all there's 12 blocks per round. This is 6 seconds, so that's the longest this could be if one node fails. And this doesn't happen very often. I think it's like 0.03 or 0.003% of the times this happens.
So how long was the round again?
So a whole schedule is 21 block producers. This is how delegated proof of stake the default is. 21 block producers with 12 blocks each at half a second. So that's about 2.1 minutes. Each block producer has 6 seconds of blocks to create 12 blocks in.
So in order to make sure that my transaction will be on chain, does it work also like the term that I can just increase gas? Because here...
Yeah, we're going to get to account resourcing in a bit. But what's important to realize here is that if your transaction did get included here in number 4, it didn't actually get put in for it. It didn't actually get added to the blockchain. But that transaction will invariably get ended up putting in one of these, right? That should almost always be the case. There's like such a statistically low possibility that it won't get added to the blockchain, even if the block it originally gets confirmed in is missed. So those 2 blocks that they created are unpaid for, right? Those 2. So these block producers are highly incentivized to try and create, very low latency connections to each other, and have good internet connections and such. So now what about when you have malicious parties in this system? Either somebody attacks nodes and compromises it, or a node themselves wants to attack the network. So this is something that a blockchain can deal with. It can deal with a certain tolerance of having malicious parties in the system. So if we have a malicious minority, a minority being two nodes in the system, two nodes can compromise the 3 out of 4 consensus. So they can create extra forks, and during this extra fork, they can try and convince something that something else happened that it shouldn't have. But really, basically over time, that fork, and actually very quickly, that fork will be thrown away by the rest of the block producers who don't synchronize it. They can keep doing this as long as they want. Basically, nobody will keep looking at this chain because they'll see this one's the longest with the most irreversible blocks. You can also create, two sets of blocks with different transactions in them or different orders. You can still validate the rule, but quickly and eventually, the rest of the nodes will synchronize the longest blockchain, and those transactions or those blocks will not be considered part of the blockchain quite quickly. So you can have network fragmentation where several nodes in the network can go down or have connections which, again, eventually the longest chain will emerge once they come back in connection, unless perhaps a majority of them go down, which is unlikely. But if a minority of them disconnect, then the network will still recover and synchronize. So what if we have a corrupt supermajority? So in our case, we need 3 nodes to be corrupt for this to happen. In the US, it would be 15 nodes, which is quite a lot of different entities to bribe or convince to do something against their own system. Let's just do it for the sake of understanding. So they can create duplicate forks. So now these 3 here, 1, 2, 3, are all colluding against the network and creating a duplicate chain. Now what's going to happen, there's one node in this network that's not colluding, that's this one. As soon as they create the next round of blocks here, they will set up the longest chain, and the rest of the network will know which fork to go off. So the minority can still confirm the longest chain.
Why does that one take ahead? For any reason?
Because now it's this block producer's turn to produce a block again.
Yeah,
And this one is not endorsing that duplicate fork.
Oh, because it's not endorsing it.
Yeah,
But how do you know? How does it select to not endorse it?
Because it just doesn't agree. It's looking at this blockchain. It's looking at this history, and it is agreeing with these rules. So as soon as it agrees with the set of rules here at this point, because it's their turn, they then determine which history everyone else will synchronize to. Up until this point, it's ambiguous.
Okay, but how does this party actually come to this decision? It's a program that actually puts it.
Yeah, the program does it. So
the program does
for this scenario to really happen, these 3 players would have to modify the software to create 2 separate blockchain histories at the same time. They can do this. Nobody can stop them from running different software, right? So they would configure their software to create a different history with different blocks and transactions, receiving the same transactions from the rest of the node as everyone else, but a different history. They might just, for example, omit one account's transactions that they don't like, something like this. But then what's important here is the minority can basically resync the network so that even a supermajority cannot attack it. As long as there's still small parties, the network can still synchronize and know which chain is the best one.
But how would that party know?
So this party this party is just running the correct software. They just have to confirm one of these chains.
Right, but...
And then it still allows the network to come to consensus.
5 seconds of block going on, right? Let's say I'm one of these parties, and I hire you as my blockchain engineer, because I have no idea what's going on, so I'll just let you do it.
Yeah.
Let's do a realistic scenario, right?
I mean,
And these 3 parties change their code and start running 2 chains. well, it would take you some time to figure out what the fuck is actually going on, right?
No,
About that time.
if you run the node software provided by EOS.io, it will select one chain and therefore create consensus back to the same point.
Oh, and you don't interfere at all.
No, it will do this. It knows that it doesn't want to run two histories of the chain. It will use this logic, the three rules, to select one chain, so that everybody. The whole point of this is so that everybody runs the same history.
Yeah, I get that.
So it will do that automatically. It might see two chains and select one, maybe arbitrarily, or maybe because one of them doesn't use the right rules.
Well, what if
If these parties are not conforming to the rules in the protocol, they won't sync at all. But they can still create blocks that conform with the rules, but perhaps omit a few transactions. Then this party can still confirm the one that they want to and add those transactions that these parties are blocking.
It's such a short time to in case of an attack, like if you want to change something, I think you already lost this.
Yeah, I mean, the game theory is a bit. I mean, the game theory is that it doesn't make much sense even for a supermajority to attack a network because they lose so much value if people realize what's going on. Unless they're anarchists or something, yeah. Yeah.
Oh, okay.
So these malicious parties could, convince people about different histories up until this point, really, and then at this point, everybody else will sync the longest chain, and nobody will be confused anymore. So one thing that a malicious minority can do is that they can stop the last irreversible block. This is an attack vector with EOS.io. So a minority, so just two parties, as long as they keep not producing blocks, then there'll never be consensus on the last irreversible block because you need 3 out of 4. And if 2 of them don't participate, then that last irreversible block, the irreversible one, never gets finalized. So that is a bit of a problem for some applications that depend on that irreversible block, but for a lot of apps it doesn't. So this chain will still keep running until these two participate again.
One question. In the order, you said first that the agents get selected by alphabetical order.
Mm-hmm. The transactions, the block producers are put in a schedule alphabetically. Okay. That's the default configuration.
So someone can think about it and position themselves always like on the third and fourth position too.
Yeah, but you can't change your account name once people have voted for you. So these guys create an account in the system like you guys did. They can't change that ever. Oh. So once people have voted that account in, they can't change their order. Yeah. People have tried to do some interesting things where they order it based on location to try and optimize connections. So people in China will be next to people in China. People in Europe will be kind of, the synchronization happens across the world latitudinally. It's theoretically possible. Somebody's tried it. Okay, so now we're going to go into the cryptography that allows them to synchronize. So who here is familiar with the hash function? Cool. So we're going to do a small demo, I think. So this here is a hash function. It basically gets an arbitrary amount of data. Right, here's my data. And it creates a summary of that data here. So this is the hash of that data. Now what's important here is that every time I put in the same data, so if I remove A and then put in A again, then it will always come to the same result here. This is a one-way function, so that with this hash, I can't get back to the data. With the data, I can get the hash. So it's a one-way function. It summarizes it in a way that's deterministic. Every same data will create the same hash, and this hash is a finite width, a finite length. So this is always the exact same size. So it creates an unforgeable small summary of data on the blockchain, of whatever that data is. So the way that's used is that, so this is the data that's actually in the box in EOS.io. This is not all of the data. If you want to check it out, you can see what data is in the structures here. So that data has a few important pieces in it. Firstly, it has the producer who signed the block and the new schedule. That's new producers. So new producers is the next schedule. If that changes in a block, then it will be put in new producers, so people know that there's a schedule change. There's also a summary of all the transactions and a summary of all of the actions. Okay? And also the hash of the previous block. So now all of that data, the hash of the previous block, the transaction summary, the producer, the new schedule, and a few other bits, is put together and hashed. And that creates the hash of this block here. Now what's important in this structure is that the next block links to that block through its hash. Make sense? Yeah? So what's in the transactions themselves? So this is the transaction receipt. So this is the transaction after it's been executed. So it has a reference block hash, so a recent block header. If that's too old, then it gets rejected. It's invalid. It has an expiration. This is usually about 30 seconds. So if this has existed for more than 30 seconds, it's also invalid. That prevents people sending the transaction twice to the blockchain and it getting included twice. It puts the identification hash of the chain itself, so you can't send it to two different blockchains. You can only send it to this blockchain. That's the only place it's valid. And it has a list of all the actions that it wants to execute. So that's what the authorizer sends to the blockchain. And then once it's executed, the block producer creates this receipt. The receipt has the status of whether it was successful or not and how much resources it's billed for. So that's added by the BP. So this is the data that's put into the block in a specific structure called a Merkle tree, right? And the way that's done is you create a hash of the transaction, and then you create a tree of all of the hashes that are being added to the block. So the way it works is I create a hash of the first transaction, that's this. I create a hash of the second transaction, that's this. Then I hash these two together, that creates this one. Then I get the third transaction, create the hash of that. Fourth transaction, hash of this, and create the hash of these two. Then I create a hash of these two, and this final summary summarizes every single transactions that happen in the block. Now why this is useful is that it summarizes every transaction into a tiny piece of data. And the only way to get that hash, this called the Merkle root, is to have all of these transactions in order. And all of those transactions have the action data that they execute as well as whether they were successful or not. The other useful thing you can do with the Merkle root is you can create a proof that a certain transaction existed in it without revealing all of the other transactions. So if I provide somebody with just this data, I can actually confirm that this happened in a transaction Merkle tree without revealing any of the other transactions. So this is useful creating proofs that a transaction happened without having to reveal the entire block data. So this creates the ability to create efficient summaries, efficient proofs without having to have the whole block data provided.
How does it do that?
How does that do that? So I have the Merkle root already, and I then get provided all of this data. So then I go through, I hash this, create that. I'm provided this one. So then I get these together, I hash it. That gives me this. I check.
Right,
then I hash this, and then I check that against the block header. And then if it's the same, I know that this transaction happened in it without actually having to provide all of this other data. So it allows smart contracts or external people to verify the transactions happen without having to put a whole amount of data into it.
Just notice that the hash zero has those two children connected to it, so it knows which other hash to take in and check. Yeah.
Sorry.
So yeah, I mean, you start off with just one transaction, but then after that you get to its hash, then it knows hash zero, has those two other hashes connected.
Mhm.
It has a, let's call it a sibling.
Yeah, I mean these
siblings.
trees kind of organize themselves with algorithms, so you don't have to generally know all of this stuff. Sort of, yeah. Computers do it all for you, usually. So now what we can do is that we have our transaction, including whether it was successful or not, what resources it used. We can get a summary of that, and that is what's put into the block header. That's part of what's summarized in each hash. Right now, these are two different nodes here, one node and the other node. If somebody changes but one transaction here, the transaction Merkle root will change, and the final hash for that block will be different. And that will change the previous hash to the next block, which will invariably change this hash. So this allows blockchains to easily and very efficiently check if they have the same version of the blockchain as another one. Right?
Also allows the network to reject something without even knowing its
Yeah,
contents.
exactly. So I'm able to synchronize other blockchains and detect if they have the same version of mine. The only way to get this hash, the only way to have that hash, is to have the correct transactions. So this also proves that I have seen all of those transactions in this order, the same as everybody else in the network. Boom! This guy's impressed. It's like, oh! Yes!
Seems too simple.
Yeah. Well, this structure took until Bitcoin for somebody to kind of to put together with a bunch of economics as well, make this happen. Yeah, there's more data in here. It actually took me a long time to figure this out. Nobody else has actually published the block data structures before me, and I think nobody else even teaches it still. So no, it's not something that's taught by anyone else.
It's a really good concept. Like,
if you want to get the full you can go to my previous workshops, and then you can see all of the data in the blocks. Yeah, this is all of the data. There's quite a lot more going on behind the scenes, but this is the important stuff for you guys to know.
Yeah, in my trainings I just do this part.
Yeah.
You're right.
So you have a summary of all the transactions. If somebody messes but with one of those transactions or the order or anything, everybody else can detect it and synchronize away from them or not synchronize their data. So yeah, like I said, for me to accept somebody's block, it needs to pass all of the rules. It has to have the right block structure with the right summary of the transactions in the same order with the same execution status. It has to check that all of the transactions have the exact same data structure. The signatures are valid. There's ways to detect if it's on a different blockchain or not. And then I'll accept the block. Cool. So the last issue that comes about with consensus is kind of determinism and how to manage resources. So what if the smart contract has this in it? Yeah, so this will execute forever. How do they come to consensus on this? What about this one? If it's raining in London more than 3 millimeters, then throw an error. Well, let's just assume all of the nodes in the network have some source to determine the rain in London. But what if those sources differ? What if they have different, sensors or measurement units or whatever it is? Then they can't all agree. They can't all come to the exact same result. They can't come to a consensus as well. So this is here from the multi-index table API in place. So this will add a row to the table. What if we want to add 3 terabytes of data to that table? So that's not going to fit in most computers' RAM. Or if I want to send a photo in the transaction, just the raw data, it's a gigabyte. Can you synchronize a gigabyte in half a second? No, I don't think so. Not with most computers. So these are all like limitations of the hardware on the computers. And this is why there is a whole resource management and accounting system to prevent people using more resources than the system exists, so that the network can come to consensus in a decentralized way. Otherwise, it would be impossible.
So that's like a limit and putting like kind of the gas.
So,
But if you run a private network, you could increase this.
yeah, we're going to get to this in a sec. So EOSAO defines 3 different resources at the moment. So one is a CPU. It's a measure of exactly how many microseconds the transaction takes. There's a RAM in bytes. How much storage in RAM is the contract or account using? And then net is a measure of the transaction size, like what data is in that transaction. And there's a whole accounting system about how much of those resources are you allowed to use. So that's different from the gas model. Gas model does kind of more an opcode level resource accounting. This is much more macro and has very different characteristics, I would say. But it has the same objective to allow contracts to come to consensus across the network. So lastly, all nodes have to come to the same result. That means they can't rely on random numbers, because if every node generated a different random number, the execution would be different. And it can't rely on any external services, because it may get a different response. If you look at an HTTP API, it may give a 500 error, or it may give you the results. Every time you execute it, it will give you something different. So that is a non-determinism component that can't be introduced into the system. So that is why if you do depend on external data, you have to rely on some kind of oracle to provide it in a deterministic way. So that is consensus, guys.